stimulus to and I get 2,000 muscles doing the same thing, 2,000 muscles, 2,000 muscle fibers doing the same thing, what do you think that equates to?
Big contraction.
Gross motor skills, right? Bigger motions. Gross versus I want to do this. What do you think that ratio is going to be? Really, really small. So the smaller the motor unit ratio, the more precise type of movements you get. Because if I want to go and, pick something up, I don't want my whole arm to do something like that. You want to be able to do something really small. Or your eyeball, when your eyeball's like moving all over the place, right? You want to be able to like slowly move them around into precise, tiny little movements. So that when you innervate or you send a stimulus to that motor neuron, small amount of muscle fibers are moving and contracting. So you get a really small, precise, little tiny movement that occurs. So the type of ratio, the size of the ratio is directly proportional to the type of motor skill output you're going to get. The larger the ratio, the more gross the movement is. The smaller the ratio, it's for precise motor skills. Precision. And we're almost done. Okay. Gradations of strength of muscle contractions. All right, so what does this mean in terms of you want a muscle, and you need it to do a strong contraction, and you have a muscle, the same muscle, and you want it to do a little contraction, right? We can get gradients of force out of a muscle, so how do we control that? It's the same motor neuron that we're sending an action potential down. I have my biceps. My biceps is going to lift this tiny little coffee cup, same motor neurons. Or I have this bicep and I wanted to lift this huge table, same motor neuron. So how do I control the strength? There's two ways that we do it. We control the number of motor units that are recruited in that muscle, because every muscle has tons of different motor units in there. It's got tons and tons of different motor units. So we control the number of motor units that are that we're going to stimulate. Controlling the number of motor units controls the number of muscle fibers that are contracting. We also control the frequency of their contraction, of the stimulation. We control the frequency of the action potential. All or none principle. Do you remember this? A motor neuron is stimulated. One motor neuron. All of the muscle fibers that it innervates has to contract or not contract. It can't be half and half. So if that motor neuron has a 1 to 2,000, all 2,000 are going to contract or all 2,000 are not going to contract because they're all controlled by the same motor neuron. This is applying to the muscle fibers, not the whole muscle. Because the whole muscle could have 100 motor units. So only if one is activated, however muscle fibers that are in that one is the only one that gets the contraction. Motor unit recruitment has an orderly sequence. So, I need to lift this table. Have you ever tried to pick something up and it was a lot lighter than you thought it was and you threw it, right? Because you actually recruited a lot more motor units than you actually needed. So when you start to pick something up, you start to recruit a certain amount. And if you need more, because you need more force, you start recruiting more motor units. The order that they're recruited in is slow twitch to fast twitch. So we recruit the ones that were on the top of that list are type 1, and we go down the chain to type 2A, and then we go to type 2B as the last. Now, why do you think that is? Type 1 generated how much force in comparison to the rest of them? Less. So you start out with minimal, and you increase if you need more. You don't start out with the maximum amount that you need because that's inefficient. Because then that's you throwing something. You thought you had more, that it weighed a lot more than it actually did, so you automatically started to recruit more, and then you end up throwing the thing backwards. You don't want to do that every time you go to pick up your coffee cup or something. You want to start with the smallest amount of force necessary and increase it if necessary. That's efficiency. Because these guys, the fast twitch fibers, require more stimulation. They have higher thresholds. Slow twitch fibers have lower thresholds. So they're easier to recruit. And then as the higher the threshold goes, the more you have to put in. The higher we go, we get, these are the fast twitch. They have higher thresholds, so they require more from us. So this is an efficiency purpose. So you recruit slow to fast. So what does this mean in terms of force production? This is referring to motor units that we're recruiting. We recruit small motor units first. We were going to recruit less amount. We're going to recruit our slow twitch. Then we're going to recruit more and more and more if we need it. And more goes into our faster and our faster and our faster twitch fibers. Now let's go to frequency of stimulation. At a low frequency, this is the speed of the action potential. So this is not what ones are being stimulated or not. This is within one motor unit, how fast the action potential is occurring to that motor unit, regardless whether it's slow twitch or fast twitch. This is how fast it's coming in. If it has a slow or low frequency, that means the stimulus is happening at a slower pace. It's definitely not this slow, because then we would never make it anywhere. It's, just slower than normal. This allows the cell, the actin and myosin cross bridges, to have a little relaxation before it keeps going. So it's a slower type of contraction. We need that motor unit, regardless of being slow twitch or fast twitch, to contract with more force. We increase the frequency of its stimulus. So we increase the frequency of the action potential. Just means it's going faster and faster and faster and faster and faster and faster. We're increasing the velocity of those contractions. This caused something that's called tetanus. You guys remember that? Not tetanus shot, but tetanus, where the action potential plateaus. Maybe, sort of. You will sometime. It's when the action potential that goes up and down. It's going like this, and it goes faster, and it goes faster, and it goes faster, and it goes faster, and then all of a sudden there's no time for there any pause in between contractions, and it starts to plateau. And these are kind of like twitches, right? When you get like a contraction that will not let go, like Charlie horses. That's tetanus. But you can do that without there being like that much pain. You can do that without causing a cramp. The cramping is tetanus. It's when the action potential won't relax. That's how you can get more force.
I know there's different types of tetanus. So
what's
the difference between, I think it's unfused and fused tetanus? Is that what it
The fused tetanus is going to be the cramp.
is?
Unfused is more about what we're alluding to here, where we're not cramping, we have really the fastest contraction we can possibly get, not allowing the muscle to really relax in between, just in high velocity. That's more of an unfused. But the action potential looks similar, it's just a little bit more bumpy, versus the cramp or the Charlie horse tetanus is like flatlined. They will not let go, right? It's like cramped for those 2 seconds, and then eventually it will release. But that's how we can increase force. So we can increase the number of motor units, and we can increase the frequency that we're stimulating in that. And that changes maximal types of contractions. So if you need maximal contractions, you recruit as much motor units as possible at the highest frequency that you possibly can.